I will be talking about the work I've been conducting over the last several years at Caltech before moving to Central Nantes. And let me start by acknowledging my co-authors for this work, Professors Aris Rosakis and Nadia Lapusta. As you all know, in this group, earthquakes occur as dynamic frictional ruptures along pre-existing faults in the earthquake in the Earth's crust. And the main tools to study earthquakes are seismic inversions and numerical simulations. However, both of them are based on assumptions that may or may not be satisfied in real case scenarios. At the same time, friction also plays a key role in rupture propagation, in key dynamic rupture issues. And it is a key ingredient in numerical simulations. For example, here at the bottom, I've got some examples from the Lapusta's group, where certain earthquake scenarios are reproduced. This is a cross-section in representing a fault, and various frictional properties are assumed about the fault. So the scenarios that come out of these supposed rheology are the result of that. So it's really important to get the rheology right in order to get physics-based models of earthquakes. So all of these points out to the need for well-instrumented laboratory experiments that can reproduce the basic underlying physics, but can still maintain enough simplicity so that clear conclusions can be made out of it. In this presentation, I would like to introduce you to our laboratory setup and then show some full field measurements that can allow us to gain understanding into dynamic rupture behavior and also friction evolution. Under the assumption of constant normal stress, time allowing, I would also like to say something about the cases where the normal stress is not constant but varies rapidly. So all of this is going to be done with analog materials. But I would also like to conclude the talk by saying what happens when using rock into the interface, into a new hybrid configurations that we have developed. So let me start by showing you our laboratory setup. So here we have the specimen at the center, unloaded in the vertical direction. So here you can see the specimen with the vertical loading, which and basically the faults are represented here by inclined interface made by two quadrilateral plates put into contact. And the vertical loading results into a resolved level of normal and shear stress on the interface. And ruptures are nucleated by the small burst of a nickel-chrome wire placed across the interface. And then using a high-speed camera here, we can, which can go to very high speeds, up to 10 million frames per second, we can observe a portion of the interface, which can be either small or large, depending on the type of observations that we want to make. And we'll deal with the sequence of images in the way that I will detail in a minute. We also have laser velocimeters that can measure very accurately time histories of particle velocities at discrete points within the region of a sample. We also have a set of strain gauges which may be used in selected cases. In making earthquakes in the laboratory, why do we use analog materials? First of all, the configuration that we have in mind here is kind of representative of a fault such as the San Andreas fault, so it's a transform fault, but we can also use it for other configurations such as trust faults, as I will detail in a later part of the talk. So it's an idealized configuration. And we use analog materials because there are several advantages, such as the fact that they're brittle like rocks, they are transparent, which may allow us to look into the specimen. But most importantly, they have a much lower shear modulus compared to rocks. And this is linked to the fact that the nucleation length scale is scales with the shear modulus of the material. It also depends on some frictional properties, and it's inversely proportional to the normal stress. But having fixed all of these parameters, it really depends on the shear modulus. So this means that for rocks, we have rocks have a shear modulus which is 25 times larger than analog materials, and as a consequence, the that if we want to observe well-developed dynamic ruptures, we should have a specimen which is several times the nucleation length scale. And this is very tricky to achieve with rocks. There are certain laboratories around the world that have achieved this, such as at USGS, at Menlo Park, at Cornell University, the setup by there are other rock setups in Japan, but they all come with their complications due to the size of the specimen and to the handling of the specimen, and also to the amount of things that can be observed. So one advantage of this setup is that we can observe a lot more. Before I go on into the details of how we observe things, also that produces kind of a sparse and rapid nucleation, but we can also have various other types of nucleations. For example, this is a developed version of the setup. The picture I was showing you earlier was taken from this side. This is taken from the opposite side. This is still the specimen under the press, and here we have developed a and also with the aim of studying the effect the nucleation procedure on the now this circuit allows to control very accurately the pressure time histories introduced onto the specimen's fault, so that we can pressurize the interface very rapidly, so in a matter of milliseconds, or very slowly in a matter of tens of minutes. So this is done by the fluid. The wire would be even more of a rapid time scale than the one showed here. But these allows us to see the effect of the loading during initiation, and the transparency of the specimen also allows us to study fluid diffusion along the interface and a whole set of other observations. So I just wanted to do a little like a brief diversion on these other topic that one could branch off and study separately, but I won't say more about this in this talk. Now, let me concentrate on what we can tell about dynamic rupture and friction evolution. And I would like to say a few words about the diagnostics. So I was saying that we have a high-speed camera that takes images of the specimen surface, and then these images contain a characteristic texture that result into characteristic gray level signature, which can be used in order to correlate these digitally, these images, so that the displacement field can be reconstructed pixel by pixel. What we have here is the displacement fields in the fault parallel and fault normal directions. And a scale here is in microns. So as you can see in the top images, we have like a displacement the fault in the direction parallel to the interface as expected, but at the same time also the fault moves first upward, as shown by this red blob here, and then downward. Now, what we do is that with these displacement fields, most importantly, is that we differentiate them spatially to get stream fields, or temporally in order to get the particle velocities. And we will be showing a lot of them later. But then using constitutive properties, we can get stresses out of strains. And from stresses on the interface, we can get friction, which is one of the key quantities that we want to study with these measurements. Now let me focus on this part of the talk about the full field characteristics of dynamic ruptures. It's important to study both subrelli and supershear ruptures because, well, subrelli are very frequent subrelli propagation is very frequent for earthquakes. Supershear is less frequent, but when it happens, it's very damaging. And there are various examples of supershear ruptures as shown in these pictures. Supershear ruptures are characterized by the coalescence of shear wavelets emitted at the rupture as the rupture propagates, which form shock fronts. Now, these shock fronts were observed in the laboratory for the first time a number of years ago in the lab of Professor Osakis using photoelasticity. But these measurements did not allow to quantify accurately various other quantities. So they were kind of semi-quantitative measurements. And so this prompted the development of more quantitative measurements, such as those obtained with digital image correlation, which I got involved in the last several years. Let's see what happens when a rupture propagates at subrelli speed, but with the speed approaching the Rayleigh wave speed. So in these panels, we have the particle in the fault parallel and fault normal directions, respectively, on the left and right hand side. Scale here is in meters per second. And so black means no motion, and then we have like red and blue in the opposite directions. And in the bottom panels, we have the same quantities reported right on the interface. So you can see that as the rupture enters the field of view from the left-hand side, we have some compression and dilatational fields. At the same time, there is also a motion in the direction perpendicular to the interface. Let me actually stop here on a frame. Here, time is in microseconds, so typically rupture takes about tens of microseconds to go through the field of view. And so here this is the rupture tip. Here are the compressional dilatational lobes that extend in front of the rupture tip. And there is an important component of the which can be even larger than the fault parallel. So this is a little bit less counterintuitive because you'd imagine that the fault parallel component to dominate for a mode 2 rupture, but this is not the case for subrelli ruptures. Now for a supershear rupture, so these are the same panels. Scale is still in meters per second, but note that the scale here is increased from 1 to 8 meters per second. Now the rupture still enters from the left. You can see that the rupture tip is here, and the dilatation and the compressional lobes are trailing behind. Let me stop to a time shot here. So you can see that these are the dilatation and compression lobes. And because the rupture has exceeded the shear wave speed, here we have shock fronts forming and extending from the rupture tip. They become even more evident if we zoom out, and then they'd be sharper than this. Here we are concentrated to understand the near field characteristics. Now, there is also richness in behavior in terms of the fault normal velocity that is first positive. So first goes, so in the subrelli case, it just went down, whereas here it goes first up and then down. But the magnitude is lower compared to the fault parallel velocity. As you can see here, scale is, up to 2 meters per second. Here we go over 10. Actually, to make a comparison between the two cases, we can look at these plots showing the velocity magnitude for both cases. And in the both panels, we can trace the time history of the particle velocity, and so trace it as the rupture swipes through. So we can see the rupture here entering the field, the magnitude increasing, and you can see the components of the parallel normal direction, with the normal component dominating the particle velocity. If we look at the velocity magnitude of supershear ruptures, we can see that it's the other way around, where the fault parallel component is much larger than the fault parallel component is much larger than the normal. And so these observations have implications for earthquake hazard assessment. First, because there are different type of motions, different magnitudes, but also because in the case of supershear, typically a supershear rupture is followed by a subreli rupture. So it means that we have both this characteristic and the one of the subreli rupture, which is kind of even more challenging for structures. Okay, so let me now move on to describe friction measurements. So clearly friction is key to the understanding of many earthquake physics problems, and assumptions about friction have implications for various issues, including energy partitioning, rupture modes, stress levels on faults, and many other things. And yet friction is one of the least characterized variables. So that's why it's important to make accurate measurements. Now, what I'll be showing here are non-traditional measurements of friction. So typically you might have heard before about measurements done in double direct shear setup or rotary shear apparatus. Now, while these measurements are valid, they typically do not have spontaneous rupture propagation, and friction is measured remotely. Whereas here we have spontaneous rupture propagation, and we measure friction locally on the interface. So here we have the shear stress field of a dynamic rupture propagating through the field of view. So scale is in megapascal here. So you can see that we go now. Oops, let me actually, the panel here at the bottom traces the shear stress along the interface. And you can see that you can look simultaneously these two plots. So we can see that this pinky area is basically the pre-stress level, and then this blue area is a peak in shear stress, and then we have a drop, and then we go to a residual level. We can then trace like what happens at a point along the interface, so we can trace the time history, and we can do the same for the normal stress. And then once we get the ratio, then we have friction. If we plot friction versus characteristic variables such as slip on the interface, then this is what we get. So something that as a characteristic, decay, a slip distance, and then a characteristic dynamic friction coefficient. So really, this is very similar to well-known linear slip weakening laws, which have been used in numerical simulations for a long time, because they're very easy to implement, they're very convenient. And so now the idea is to verify this law for a set of experiments where we, so this is the initial experiment, lower loading configuration, where we get qualitatively similar time history, but lower magnitude in terms of slip rate. Then we should get the same for a linear slip weakening law, but that's not what we get. So we get different characteristic slip distance and a different dynamic friction coefficient. So this means that a slip dependent law cannot be used universally. From one rupture scenario to another. And so the analogy to fracture and friction here breaks down. So if we plot friction versus slip rate for the two cases, clearly we get two very different curves that show the importance of the slip rate and its history on the evolution of friction. So what we can do is we can start using rate and state friction laws where friction depends logarithmically on the rate of sliding and on the state, where the state variable is typically given by an evolutionary law. This is an example. This is the so-called aging law, but there are various others. And so with the rate and state laws have been known for several decades, and they've been used to, well, they really came up as empirical laws to explain where one would slide at a constant velocity v1, and then when increasing the velocity to a larger velocity v2, you would typically get an increase in friction, and then an evolution over a characteristic length scale here, indicated as L, and then evolution to a steady state, which could result into either lower friction, which is basically a velocity weakening, or higher, and that's a velocity, so-called velocity strengthening friction. Now, rate and state can also produce an effective linear slip weakening law, and at steady state, they are also purely dependent on velocity. In fact, the steady state form is just the friction depending logarithmically on the slip velocity. So the first game we can play is that of getting the steady state form of rate and state friction, and try to use it with the steady state of our measurement. So just this cloud of points here. So that's our steady state, and so we can plot this cloud of points in the steady state diagram where we have so this is so know the difference of the slip rate in top and bottom diagram. So here is actually the real-time slip rate, whereas what we have in the top diagram is not real-time, it's just the steady state value of slip rate, so what is attained here, and also for the vertical axis is real-time friction. So then these two cloud of points map out here, and then we can add other measurements from other experiments conducted over different loading conditions. And also we can incorporate tests done with the traditional direct double with double direct shear apparatus. These were conducted by Kilgore and Beeler a number of years ago. And so we can use these low velocity measurements in order to get the rate and state parameters and see whether with these rate and state parameters we can predict or whether our measurements are consistent with the rate and state law. And in fact, they are not. So this points out to a higher, more pronounced weakening. So flash heating friction law is kind of a good candidate law. And in flash heating, what happens is that contacting asperities heat up and weaken. And this produces a much stronger weakening. It's no longer logarithmic, but it's a 1/v weakening. So historically, flash heating friction laws have actually been proposed in the context of tribology, in fact, by Ashby and Molinari and others. And then they have been kind of proposed to the earth science community by Rice, Beeler, Tullis, and Gosby later on. And by and large, they've been found to be like good candidate laws to explain weakening. So in this form here, we have this F naught could also be replaced by the friction coefficient given by the rate and state law. And so we can produce a combined version of the two laws. And also we get this steady state version of the law. And now we can start using the steady state version of this law in this steady state exercise, where we use the low velocity measurements in order to calibrate it at low velocities, and then let it evolve at higher slip velocities. So if we test this law, then we see that indeed our measurements are consistent with the flash heating, which is kind of a good indication that this law may be the operating one. So a good observation is that if we compare measurements with those done independently by Goldsby and Tallis on quartzite, we can see that that they are qualitatively similar, and they indicate so that you know the same law is operating in both cases. Now, one key difference between these two sets of measurements is that our measurements I was mentioning earlier are done for a spontaneously evolving dynamic rupture, and they are taken right on the interface, whereas these one with rotary shear apparatus have an imposed velocity, so it doesn't evolve spontaneously, but there's the motor driving it. And the forces are measured far away from the interface, then friction is kind of deduced. Okay, so we can also play the same game of testing this law, but taking the full version of the law without steady state, where we plug in our time history. And then we compute theta evolution from the slip velocity time history. And then we can put some constraints. For example, we can constrain A minus B using the low velocity test, and F star and B star likewise. And we can constrain FW and VW by the steady state analysis that we did earlier. And then we can try to fit for A and L and see whether we can find a suitable fit to these measurements. And what happens, so if we look at friction versus slip, here slip is in microns, and friction versus slip rate. So these are the experimental curves. Now, if we put in what would be predicted by this law, slip velocity, this is what we get for the retained state law. So it doesn't have just enough weakening. But flash heating can produce all of the weakening and basically matches very well with measurements. Now, all of this has been done with the assumption of constant normal stress. I would like to briefly mention what happens when normal stress changes very rapidly. So experiments have shown that if normal stress changes rapidly enough, so it's a type of different set of experiments, the so-called the pressure shear plate impact test, traditional set up by Prakash Clifton, that used it in the 90s. So during an impact of a plate against a specimen, there's a normal stress changing very rapidly and the shear stress that lags behind. So when this happens, then the shear stress to the normal stress. And so we can test this hypothesis by using the same configurations we did before, but now looking close to the free surface. And by the way, this observation is representative of what happens in thrust poles. So let us see first the particle velocity measurements. So here we see the rupture coming from the bottom and the free surface is the top. So the rupture arrives in pinches on the free surface. Then we have so this was the Supershear rupture, and here rupture coming from the again from the bottom. And when here it is, and when it reaches the interface, the free surface, it interacts with it, and so this breaks even further the symmetry. So if we look at the evolution of shear stress and normal stress, now in mega scale is still in megapascal. So this is the same thing we would see typically with a rupture in the bulk, so symmetric field. But now when the rupture hits the free surface, so we have important reductions, but also we see that the symmetry breaks down. And more importantly, this is what we observe for the interface normal stress. So let me stop here. So this is how it would look like for a rupture in the bulk. So it's nearly anti-symmetric. field. So black here is no change in normal stress. So about 12 MPa is the level of pre-stress on the interface. And so for a rupture propagating the bulk, normal stress stays constant. Now we'll see that when the rupture hits the free surface, then there are this blue portion, which means reduction in the normal stress. They happen on the time scale of microseconds, so they are pretty rapid. So this is the full sequence of shear normal stress. But as I was pointing out here, we have the reduction in normal stress. So if we look at the shear normal stress evolution with slip, then we can see that important variations in the normal stress that are not expected in a case where, and also friction has these important variations. So if we now use the same procedure as I discussed earlier to fit this experimental curve, then with flash heating combined with retain state, we fail miserably. We cannot capture these features. However, if we introduce the Prakash-Clifton formulation, where we do not assume the shear stress is proportional to the normal stress, but we take that it depends on a function psi, where the evolution of psi is given by this relation, which depends on the slip velocity and on a evolution distance, which is the Prakash-Clifton length scale, and then on the difference between psi and the normal stress. So that at steady state, then when psi dot is equal to 0, then psi is equal to sigma n, and then we recover Coulomb friction. But during rapid variations, then this difference makes it so that it's a different law, really. So now if we implement this law, then we can see that we can capture a lot better the measured behavior. And if we account for the dependence of VW and FW on the normal stress, even better the measured behavior. Now, the most important thing is that we can, and actually note the separation in length scale between the retain state and the Prakash-Clifton. The most important thing is that we can fit this parameter for a given test, and then we can produce a variety of tests and measure different friction behavior, and then use the same fitted parameters and different slip velocities obtaining in different cases, and see that if we input this slip rate history in the friction law, we can match pretty well the recorded measurements. So that's the indication that this law is actually doing pretty well. And so the important thing is that this is relevant to quite class of problems, but from the point of view, earthquakes is certainly important when we have ruptures approaching the free surface, and so in the case of fast and normal faults near the Earth's surface. And so in this case is of pivotal importance to account for these effects, but also when and non-planar interfaces or dynamic rupture in B material systems, because in these cases also there are rapid variations in normal stress that need to be accounted. Okay, so then I would like to go to the last part of the talk and focus on like a new configuration. It's a hybrid configuration, because so far we have talked about analog materials, and that's all fine, because analog materials have enough simplicity, but at the same time they're not rocks, and they may not be relevant to the study of earthquakes as natural rocks. On the other hand, rocks have the problem, as I mentioned earlier, that have a high shear modulus, and so they result in big length scales. So here we have developed a hybrid length scale where we combine the best of both worlds, where we have a analog material in the bulk, so that we can nucleate ruptures with a relatively small length scales. And once the ruptures are well developed, so they can enter a portion of the interface which is enriched with a rock quartz, in this case gouge layer. so that the rheology of the interface is controlled by the quartz gouge. Now, in this experiment, and so we have in these experiments we've used gouges with 5 microns mean of mean diameter in size. So in the results I will be showing here, the field of view is basically all within the gouge portion. So we'll see images like these ones that are completely within it. So let me remind you what a sub-Rayleigh rupture looks like. We saw it a few minutes ago. So we have the rupture coming from the left. That's its characteristic shape. Now, note that this field of view is about 16 millimeters wide. And this is purely in an analog material. Now we see what happens for a rupture propagating in gouge. So same panels, so fault parallel and fault normal velocities. With still scaling meters per second, and the field of view here is zoomed out. So before we were looking at 16, now we are about 45 millimeters in size. And what we see is first a supershear rupture, followed by trailing Rayleigh. And the trailing Rayleigh rupture resembles the sub. And then nothing else would be expected in an analog material. Let's see what happens. So supershear rupture enters, is arrested, followed by sub-Rayleigh rupture. Here we see the signature. Nothing else would happen in analog material, but here we see a rupture being nucleated and propagating along the interface, which later on arrests on the interface. And then we have other attempts of nucleation, and here we have a nucleation all within gouge that propagates and then exits the field of view. So all of these is not expected in an analog material. So what we saw was right in here is a fault parallel velocity field, with the rupture nucleating at some point along the interface. And then here we see it going rightward, and this was another event. We can map the shear stress, of course, and so we can see like these big drops, and we'll relate them to friction. And this is the second, the second big event nucleated within gouge. The way we do these experiments is that basically we apply level of pre-stress, and then we have multiple niclochrome wires here that we can use to nucleate ruptures. So we can have a first sequence and have the load to drop, then we can reload to the same level of pre-stress, and then another sequence. So these are two plots showing the spatial temporal sequence with the distance along the interface on the x-axis, and the time evolution on the vertical axis, and the color scale is in meters per second. And so what we see in both cases is qualitatively similar behavior, with an initial supershear rupture attempting to enter from the left and being slowed down or arrested, and then a sub-Rayleigh rupture coming from behind, and then and again being arrested, and then various other events being triggered at various points along the interface. To make sense of this, let's concentrate on one of these sequences, and let's observe at the evolution of sleep along the interface. So as I was mentioning, so we have the first event coming from the left and being arrested, and then the trailing Rayleigh, and then one dynamically nucleated rupture, and then an attempt of nucleation, which failed, and then we have another dynamically triggered rupture. So if we now map friction and slip rate versus slip for event by event, we'll try to understand what happens to friction evolution. So here we have, with the arrival of the first supershear rupture, and you can see this blip in the slip rate, we can see a friction just increases. So slip rate reaches nearly 2 meters per second. It's just below it, but there's never a weakening here. There's just strengthening. Now, with the arrival of the trailing Rayleigh rupture from, so here's the strengthening, we have the weakening, and then we have a re-strengthening later. Then with the third event here, emphasize this one in blue, we have similar stories: strengthening, weakening, and then healing. But note that the drops in friction are pronounced, so they are kind of not consistent with just logarithmic weakening. And so the other thing to observe is also the strengthening that occurs in here from event to event. And this strengthening is quite large. It is not consistent with the direct effect of retained state, because the retained state direct effect will produce much smaller strengthening, and also it would occur nearly instantaneously, nearly with zero slip, whereas here it happens on the same slip scale as the weakening. So all of this really points towards the behavior of gouge being consistent with a strengthening rheology in terms of retained state, that then results into a flash sheeting, so in enhanced weakening. So the weakening really is not because of retained state, but it's because of enhanced weakening mechanism taking place. Now, this story was done at one location across the interface, but we can take a different location, for example, this point here. And then at this point, we don't see much of the first events, but we see most of the last event. And again, we see, this big strengthening and big weakening. So, so then we were looking at the slip, well, at the friction versus slip, but we can also trace friction and slip rate time histories. So we're at these different locations. So we see, the 3 events at the first location and the 4th event at the second location. And now we can plot friction along the fault, and we can plot various time histories. So we have basically nearly a continuum of time histories. And so here we have an intersecting plane with this topography, which traces a time history. And so if we get the plane moving here, we form various time histories as we move along the interface. So what this complex topography indicates is kind of complex, friction evolution. You can see that these peaks here in red indicate strengthening, indicate barriers to rupture propagation. But these barriers can be overcome, and they can give away to dynamic rupture propagation, which has these valleys here indicated in blue. So we have really come a long way from the simple notion of friction as weakening in terms of linear slip weakening, but even just a simple evolution. It's really much more complex phenomenon that depends on a number of rupture complexities. So here we have the friction topography spinning, revealing all of the complexity. So I guess that I can wrap up, so to leave time for some questions. But to summarize, this last part of the talk, I'd like to point out that these laboratory ruptures in gouge propagate through like a region of gouge in a fashion intermittent propagations. It's not continuous, but like various events that stop, they are rest, and then they are renucleated in these triggered events. And the key thing is that gouge here behaves as a barrier to dynamic rupture propagation, consistent with the strengthening of friction. However, as dynamic stressing associated with the rupture continued propagation in other parts of the sample, then dynamic weakening can be activated, and when it is activated, then it gives rise to dynamic renucleation, which is a form of dynamic trigger. And so, so these findings indicate that so they have important implications for earthquake hazard, because they imply that you might have a barrier, a patch in a fault, such as the Parkfield section, that may be considered immune to dynamic rupture propagation. However, if these enhanced weakening mechanisms can be activated, then dynamic rupture can take place and the barriers can be accessed.